What if the particles we see, electrons, quarks, photons, aren't the most fundamental building blocks of the universe? What if instead they are tiny vibrating strings, each with its own unique tone, resonating through a fabric of reality woven from more dimensions than we can perceive? Welcome back to Infinity Beyond. Today, we venture into the complex and beautiful realm of string theory, a contender for the theory of everything. At its heart, string theory proposes that all particles are not point-like dots, but rather one-dimensional strings. Depending on how a string vibrates, it manifests as different particles. One vibration might appear as an electron, another as a graviton. These strings are unimaginably small, far smaller than any particle we can observe. If an atom were the size of Earth, a string would be about the size of a tree. But here's where things get even stranger. For the math of string theory to work, it needs extra dimensions. Not just the familiar 3D space and time, but 10 or 11 total dimensions, depending on the version of the theory. The 5 original string theories were later unified under a larger framework called M-theory, which operates in 11 dimensions, 10 spatial, 1 temporal. So, where are these extra dimensions? They're thought to be compactified, curled up tightly into tiny, intricate shapes, known as Calabi-Yau manifolds. Imagine rolling up a 2D sheet into a tube. To someone on the surface, it looks one-dimensional. Similarly, these extra dimensions are rolled up at such a small scale that they're invisible to us. But they're not irrelevant. The exact way these dimensions are curled determines the properties of our universe. The forces, the particles, even the fundamental constants. Change the shape of the extra dimensions, and you change everything. Now here's the twist. There are 10,500 possible ways to curl up these extra dimensions. That's a 1 followed by 500 zeros. Each way corresponds to a different universe, with its own set of physical laws and particles. This staggering diversity is known as the strings landscape, or, more dramatically, the multiverse landscape. And in this view, our universe is just one of many, selected not by necessity, but by probability. Some physicists call this the anthropic solution to fine-tuning. Out of the vast number of possible universes, only a tiny fraction allow for life, and we happen to live in one of them. Critics argue this is untestable, but others see it as a natural consequence of the math. Let's dig deeper. String theory also predicts the existence of a particle called the graviton, the quantum carrier of gravity. Unlike other quantum field theories, string theory naturally includes gravity, offering hope that it could finally unify general relativity and quantum mechanics. That's the holy grail of physics. But there's a problem. String theory has yet to make direct, testable predictions. It lives in the world of mathematical elegance, but lacks experimental evidence. Some suggest we may find indirect signs through phenomena like microscopic black holes at high-energy collisions, anomalies in the cosmic microwave background, supersymmetric particles predicted by string theory but so far unseen. Others believe string theory may never be testable with current technology, and that it's more of a mathematical framework than a physical theory. Still, it's stunning in scope. It connects gravity, quantum physics, thermodynamics, and information theory in ways no other theory has. And it invites us to imagine a universe far richer than we perceive, where dimensions are hidden in plain sight, curled within every atom. What if one day we develop tools sensitive enough to detect these curled-up dimensions? What if we could map the geometry of reality and tweak it? It might unlock new physics, new technologies, or even access to other dimensions entirely. Or maybe it already has. Some speculative thinkers wonder whether dark matter or dark energy could be the shadow effects of these extra dimensions. Perhaps we are seeing hints of their presence, but lack the tools to interpret them. Whether string theory turns out to be the final theory or just a stepping stone, it has already reshaped how we think. It blends geometry with physics, space with information, reality with imagination, and it whispers of a universe more intricate and more beautiful than we ever dreamed.